So this next example, we have a beam of varying moment of inertia. As you can see, AB and BC is different, 500 and 750 millimeter to power 4. Then you have CD 600. So the question goes, to determine the internal moment at each support of the beam shown in figure 12 AA. The moment of inertia of each span is indicated. So moment inertia is given I, and there's a difference in IAB and IBC, which is different to what we've done before. We have a similar I and E. So in this one we have a different I. So we have a loading here at overhang here and 600. Just to highlight that you have an overhang here. AB is overhang. There's no support here. We have support at B, but there's no support at end of AB here. At joint at point A there. There's no. So this is considered overhang. So you can calculate your stiffness factor for BC for EI over L. L is 20. L is 20 and your I is 750. That is for BC, member BC. For member CD, for EI, I is 600. I is 600 and then your length is 15 meter. So you get 160E and 150E respectively. And then you can start calculating your distribution factor lah. For distribution factor at point B, at joint B, towards C, DFBC, from B to C. The value is 1 minus BF B to A lah, which is 1 minus 0 is equal to 1 lah. This is due to the distribution factor of BA from B to A is 0 because you cannot distribute your moment from anything towards the overhang. There is no support here, so moments cannot be transferred to the support. Basically, it will be deformed. So based on that, you have your distribution factor for BA is 0. So so the total distribution factor at point B will be 1, as we've done it before. 0.4 plus 0.6 will be 1. So the sum of distribution factor at any joint is 1. So based on that, distribution factor, summation of distribution factor at joint is 1, and then distribution factor for member at overhang is 0. So you get your 1 minus the overhang distribution factor is 0, BA 0. So you get your DFBC is 1. So basically moment at B here will be distributed towards C. A whole of moment will be distributed towards C. There will be no moment distributed towards joint A. That is what is shown here. And then for members joint B, joint C, you can calculate as before. So this is your K for CD, K for BC here. This is KBC, and then this KBC, and then this is your KCD, 160E. So distribution factor from C to B is 0.484. Then from C to D, which is 1 minus D, or you can also take from this, you get 0.516. So 0.516 going from C to D. Then D, as we all know, is 0 because we have wall here. So it's 0. You can calculate also. And then you need to calculate the fixed end moments. So due to overhang, this is overhang. So fully moment from 400, fully moment will be applied here. So 400 times moment arm of 10. So you get the moment, fixed end moment at B would be A. BA is 4,000 pound-feet, or in this case 400 Newton-feet. So let me change this before we go any further. So basically overhang 400 Newton times 10 meter, 400 times 10 meter. So you get your moment of 4,000 Newton meter, and then BC WL squared over 12. Because this is distributed load, so WL squared over 12 here, WL squared over 12 here. Okay, negative 2000 and 2000. Negative is counterclockwise and positive is clockwise lah. So you can construct your table here, join, then member. So as we said before, there is no join A, so you have join B, C, D only. So this is pin, and this is pin, and this is fixed. So you have member. There's no member here because it's an overhang. There is an overhang. There's no pin or anything support at the end of A. So this is your BC member, CB member, CD member, and DC member. Next, you can key in your you can write in your write up your distribution factor 0, 1, 4, 8, 4, 5, 1, 6, and 0. Next, you can write your fixed end moment here. This is 4000 Newton meter. At end of B, you calculate. This is 1 squared. WL squared over 12 here, negative 2000, negative 1000 at BC and CB respectively. So as we done it before, unlock. So because there's no distribution at member here, which is member AB lah. But there's no distribution, so it will be 0. And there's no moment being distributed to at the joint. A mistake. As we talked about before, you need to sum up when you have two moments at join. For example, this B here you have a moment due to that load here, this 400 Newton load, and then so you have moment due to this 60 Newton per meter distributed load. So you have to sum up. So you sum these two, so you get 2000. You unlock negative 2000, and then times 1 distribution factors, you get negative 2000 here, and then carry over half of it, negative 1000. Same also at joint C, but also you have only one moment here, which is 2000 clockwise. 2000 distributed basically plus 2000 plus 0, get 2000, unlock, become negative 2000. Negative 2000 times these two distribution factor, you get 968 and 1032 negative both respectively. So carry over, so you get 1516, and this carry over to 484. So very easy. So at this line 3 lah, this considered as line 3 lah. Line 3 CO ni, this CO, you get the distributed carried over moment that is being carried over to that joint. So you have at joint B 484 negative, at joint C negative 1000, joint D negative 116. So repeat the process. Unlock, become positive, times this factor, so you get 484. Unlock, become positive 1000 times 0.484, you get 484 times 116, you get 116. Then DC is wall, so wall times 0, then there's no distribution. Unlock kan unlock, tak kisah. And then carry over 516, you get 258, and so on. And continue this process until you get a very small amount. People will say that 2 decimal point of 0, like 0.01, and can stop. But then again, this example, it stops at 0.1. So but it is considered, it's considered good already. So you get sum up, you get 4000 here, and sum this up, you get negative 4000. Sum this up 487.1, sum this up negative 487.1, and then sum DC, you get 293.6. So these are the moments at your joint. So based on this moment, you can draw your free body diagram. So you have negative 4000 here. So you have these 587.1 here, and then 587.1, negative 587.1. Negative 487.1 here, positive 587.1 here, which is this is negative, this is positive, and this is negative lah. Like we talked about before, this is negative 293.6, which is from here lah. So you draw up, make sure you draw carefully and represents the negative and directions of the moment. Make sure. If not, you'll be you get different amount of shear. Kat sini you get different amount of shear. Um, so you solve for shear, a bit tricky to solve for shear. Ignore the pound unit. Basically, pound is Newton. I convert it up like what I did before. This is new pound actually, but I just change the unit to Newton. And feet is meter, so you get this equation. Let's say you get this the same. The value is the same. So you can draw your shear force diagram. Basically, here 0. This here is negative 400, and then up 400, and then up again 770.6, and then reduce due to this distributed load triangle, and then going up again 4 to 9.4, and then up again for 58.5, and then down 58.5. And then you can draw your shear bending moment diagram. As you can see, there is no moment here, so it will start from 0, which also identify in this analysis. So you start from 0 and increase up until negative 4,000, because there is a negative 4,000 moment here. Negative 4,000. Uh, it is important for you to remember that when you have when you draw bending moment diagram, the value of a moment here, which we denote as positive, but in drawing bending moment diagram, when the moment making that concave, like set face, not a smiley face, it become negative moment. If it is a smiley face, it become a positive moment. So in this case, cause a frown up, smile, so it'll be negative, so negative 4,000, and then it is increase, the moment increase up until this point, 949.1. But this should be based on your shear force diagram. When you have a shear force diagram of a square, then it will be a triangle bending moment diagram. If you have a triangle bending moment, a triangle shear force diagram here, like in this example, you have a triangle here because this distributed load. So you get you have a bending moment, a curve, a curve bending moment diagram. You have a peak here because there is a inflection point here of shear force diagram. That's why you have peak of bending moment here, where you have a shear force of 0, summation of shear here is 0. And then you have a peak of 7.1 here. A bit tricky, drawing this shear bending moment diagram, but it gets from the constant exercise. The next video, we're going to talk about stiffness factor modification, and then also the member pin supported at far end.